Good evening, AP Chem students. Here's a little bit of information that should help you with the acid-base titrations that we are doing. Okay, today we used an indicator, so I want to explain just a little bit more about those. We talked about pH and how that's a fancy way of measuring the hydrogen plus ion concentration in a solution. Okay. The pH indicator will change color at a very specific pH range. So for instance, the phenolphthalein that we used today changes color between 8 and 10 pH. Okay, so it's a little bit more on the basic side. So the things that are above 7, those are more basic. Things below 7 are more acidic. When we're doing this titration, we're basing it off of the theory that if I add the exact number of acid molecules, so that the number of ions of H plus are equal to the amount of ions of OH minus or hydroxide ion, that I will neutralize the solution entirely. It might produce a salt and water, but we're trying to test whether we can do this very exactly so that there's nothing left over of the original acid or the original base. Okay, we used the pH indicator to reveal to us where that point was, or something that was very, very close. And so I want to show you something, but before I do that, the graph, here is a table of some other indicators that exist. Okay, we won't have all of these in the lab. We could have methyl orange and phenyl red and bromothymol blue, as well as the phenolphthalein. I also have one that's a universal indicator, and that one should be able to do, it's a mixture of about 3 of these indicators so that it should have a continuous pH range in the different colors. So I'll explain more if you end up using that one, but you have a lot of options as far as which one should come close to your equivalence point. And how will you know? You'll have to measure the pH of your juice or soda when you get here, and we'll go from there. But until then, I want to show you something about the pH. When you titrate a strong acid and a strong base, this is what we did today. There is a way to graph this and get the information from it that we're looking for. Okay, for instance, if I graphed the base that I added by volume, so today I had you recording volumes of base from the burette down here, and this is not necessarily your readings directly, and if you had any subtractions, this would be your amount after those subtractions. Okay. On the other axis, I have pH, so from 1 to 13, or technically 14. Okay. If I had acid in the beaker, if I'm measuring the pH that's in the beaker or the flask, it's going to start pretty low because all that's in there is that acid and the indicator solution. Okay. And so that part starts pretty low. As I'm adding more and more base, this will increase. As you see, it's increasing relatively slow. But then when you get closer to where this equivalence point should happen, the amount of volume, as I can cross-reference that by looking down at this axis here, it's going to increase very fast. It's going to change very fast. So part of the reason we slow down to adding just a drop is so that we can see and spread this part of the graph out and find this equivalence point. Okay, as you keep adding that base, then eventually it'll level off at the pH of the base that you're using. Okay, so we can find this equivalence point by looking on this graph. We can estimate it by looking over here and by using this volume and calculating how many moles from that exact volume of the molarity of base that we used. There's another way using calculus, and you can technically use the Logger Pro graphs to achieve that. I'll explain that if we need to. For now, this should serve our purposes just fine. The other thing that we'll be doing, which more involves the juice or the soda that we're going to use tomorrow, is a weak acid with a strong base. So I'll be giving you a sodium hydroxide solution again, but your juice or your soda will have citric acid, which is a weak acid. Okay, and so if I'm titrating a weak acid with a strong base, it's going to look just a tiny bit different, but not a whole lot. I'm still going to start with a very low pH, and it'll increase as I add base, but you see it increased kind of fast at first, and this might even be a whole slope. It won't perfectly turn out like this shape every single time. Okay, but it'll keep increasing, and then close to the volume where the equivalence point will be, that of your adding, it's going to shoot straight up, it's going to change very fast, and eventually it will level off again. Okay, so same thing there, and we'd find the equivalence point using this area of the graph, this entirely vertical portion. Okay, so tomorrow what we'll be doing is making these graphs on the computer. So you'll be entering your volume as you go. You'll have a pH meter reading the pH for you, and we'll also put in the indicator so that you can tell how close. You'll have two ways to find it. You'll have the visual, but you'll also have it on your graph with the pH. Okay? I have one more thing I want to show you, and this is also in your textbook, but I wanted to pull up a couple of examples. You may have heard about this conjugate acid-base pairs and wondered what it relates to. So when I have an acid-base neutralization reaction, each acid ionizes in the water, each base ionizes in the water. Okay, so there's something that donates an H+, and we don't necessarily write it all out like this, but in the end, this is what it would turn into. Okay, so if I have a weak acid like ammonium ion, which is NH4+, the reason it's an acid is it donates an H+ to the solution, or you could also call it a proton donated to the solution. After it donates this proton, what's left is NH3. So this is the neutral compound ammonia, and this has now gone and bonded with a hydroxide and become water. So this ammonia, which will have decomposed on its own to ammonia, is now by itself, but it's a weak base. It has a different property than the NH4+. So anything that is an acid, after it has ionized, will form a conjugate weak base. Okay, so this would be the acid that we started with, and this would be the conjugate base, the NH3. Another example could be fluoride ion, which anything ending in IDE is a single element as an anion, which is specifically the negative charged ion. So all the halogens are -1. So fluorine becoming fluoride is F -1. All right. This ion on its own is a weak base. Okay, it's a weak base because it will accept or make a part of this H+ ion a part of its entire molecule. So when those come together, it becomes HF. So this was a base, and then after this bonding happens, it's a weak acid. Okay, so or the conjugate acid is what's over here. If you're asked about these pairs, you may have to label some of those, especially in the pH packet, which some of you still have to pick up. You'll have some pairs to identify there, and that helps you recognize things that have the property of donating the H+ ions or accepting an H+, and then how things might react in other reactions. Okay, so that gives you a little practice with that. For tomorrow, the first thing you need to do is come in and measure the pH of your juice or soda. From that, we'll have you calculate everything else, but from that pH, you'll calculate the H+ concentration, or the molarity of the H+ ions. That's the same thing. Once you have that, using the volume that you test or will be testing, because the pH will be the same no matter how much you measure in the container volume-wise. Once you have that pH and the volume, which should be about 25 milliliters for titration, you can calculate how many moles of H+ there are. Once you have the moles of H+, you can find an equal amount of the hydroxide ion, so the OH-. That same number, because there should be 1-to-1 H+ to OH. Okay, so you're going to use that same number of moles from your H+ that you calculated, and you're going to figure out that many moles in approximately 25 milliliters as well. Gives you a molarity of the sodium hydroxide solution that you will need. Now I'm only making one concentration of the sodium hydroxide, and it's going to be about 0.10 molarity. Okay, so you're going to take that and dilute it down to what you need, because you'll probably need something more dilute than that. So this, once you have calculated your desired molarity from the moles of your pH of your juice or soda, what you need to do is use the dilution equation. The M1 times V1 equals M2 times V2. Okay, so you should have everything but one variable to solve for. You have a desired, you have a molarity to start with, and you don't know how much volume you need of that to dilute it, but you do have a desired molarity and a desired volume for that molarity. So then you could solve for that V2. All right, if you have any questions on that, I will be here in the morning, but it is picture day, so please be aware that you won't find me between 7:30 and 8 necessarily, but it's possible. But before 7:30, I will be here. Alrighty, have a great night, and I will see you tomorrow.